quick.
Close call. Yeah.
Right? Half the turns, half the voltage. Okay, good. What's the secondary current?
Twice that of
Page 73.
so that's 1.4.
In this diagram.
2.4.
In this diagram.
I'm lost.
2.4.
Hold on.
2.4.
Can we start over?
This is a quick and easy answer, but I
Yeah,
got
it's
to
2.4.
Is it?
Yeah.
You sure?
Thanks for guiding me.
Anyone else have a different answer?
I got 2.4.
Maybe it's half, 0.6.
In this diagram, what's the secondary current?
I'm going with 0.6.
Zero?
Zero.
Because it's opposite.
You went
Oh,
across.
Oh, I didn't even look at it, yeah, it's not even connected.
You have free pen.
It's not connected, it's unloaded, right? What's the primary current? I don't know, but will it be big or small?
It's gonna be bigger.
Smaller.
I mean, smaller. I mean,
Well, it depends, is it hooked up or is this just like theoretical?
This is powered up with an open secondary.
well, it will be bigger than
Current
zero.
be?
Yes.
Bigger than
It
zero?
will be bigger.
Okay, okay, yes.
Still
Yes.
gets
When you had to do that during
Probably smaller
one,
than
like
that.
1.
Magnetizing current?
Magnetizing current, very small current, just to do what?
Magnetize? Set up lines
Yes.
of flux?
To magnetize, to cause the magnetic field to do its work. Okay, awesome. Now you load this thing up. Okay, well, let's look at this. Let's look at this vector diagram here. They put everything on the same diagram, even though those voltages are not actually connected to each other, because we have the primary and secondary on the same diagram. All they're showing is that the applied voltage and the counter EMF, these two here, are on the primary. That's the primary. The far right, primary. The secondary induced voltage is half, right? It was 60 volts, right, Kyle, instead of 120?
Yep.
So they drew it about halfway, but they shouldn't have drawn it over top of the same thing. It should be a separate vector, but they drew it on the same one, showing you that it's in phase with the counter EMF in the primary. So that's, I've already taught you that, nothing new there. What is little IM and flux M?
The
Magnetizing current and the magnetizing flux.
flux.
And the magnetizing flux.
That's what it said.
So the current is in phase with the flux. When the current increases, the flux increases. When the current decreases, the flux decreases.
Should it be MI and flux, not IM and flux?
It's a subscript. So,
Well, your current,
yeah.
Current magnetizing.
so no.
Alright, dude. Thanks for that.
Okay, so all that is showing you the relationship that the current is lagging the applied voltage by approximately 90 degrees. Why wouldn't it be exactly 90 degrees that it lags? Maybe 89-ish, maybe?
Is it induced
Copper
voltage?
losses?
Yes, there are small amount, small.
Is it the transfer?
Core?
Would that be copper losses?
Nothing.
Bringing out of exactly 90?
Yeah, so there's a little bit of resistance.
There's such thing as a
Effective, just say due to effective resistance,
Gotcha.
right? It might drag this back a little bit, right? And then that flux would be in the same lineup as that. Because the current increases, the flux increases, the current decreases, the flux decreases, right?
Right.
Awesome. Oh no. Oh no.
Oh no.
What?
Now I have a 10 ohm load. What's the voltage on the secondary?
60 volts.
60.
Yes.
So divided by 10 gives me 6 amps. Okay, awesome. How much is in the primary?
12.
Well,
Three.
No, it's gonna be small, it's gonna be 3.
3.
you guys are such monkeys, come on. Keep up. You were sleeping half
Okay.
today.
How's that for you? So far so good?
Is 120 volts.
Yeah.
Everything I know I've told you, okay, like about this. This is all there is to know about that. Okay, but what's happening with the flux in the core here? That's what I haven't told you.
Everything I know I've told you, we've noticed.
What's the window of the video?
All right, we gotta make sure that this is wound the same way, so I'm just gonna draw it out, wind it wind it up the way I want it.
That's my chance to escape.
Yeah, they didn't wind it right. There are 2 turns, 100 turns, 50 turns.
You
So
just copied
so I
and
did
pasted.
it this way. Okay, so if I'm saying the current is going that way, okay.
Just
It
way
looks
down,
like-
negative on the top.
I wish the Y was less clear, but why is that one this way wrong?
Because they copied and pasted it. Use it as a. Kitten caboodle? Oh my god. That's sad.
Before I connected this resistor, was the 60 volts there?
Was the term on?
If there was no load, the volts were there.
Volts are there, yeah, but no amps, so no power output. You gotta have volts times amps, and if there's 0 amps, then there's zero VA or 0 watts. Okay? Current, so if I pick a side, any side, make this polarity instantaneously this, which way does the current flow through the first winding?
Up to down.
Out of the negative?
Yes.
Yes, because it's a load, it's like a load to this source,
Yeah.
right?
Yes.
Okay.
You do the hand thing, Ron.
So, yeah,
Look.
this one? How do I, this one or which one? Right hand?
This one. The right hand's for one thing, and that's not appropriate for school.
Not till you get to level 3. Okay, so the flux goes counterclockwise through the core. That's the flux's direction, right? It has that direction. Okay,
Show that to me.
and there might be some leakage flux, remember they were talking about that. Whatever, let's try to contain it all in the core, use it 100% of it. Okay, now, I'm going to say, okay, when this is expanding, so let's kind of open up the conductor here. Say that this is the portion leaving, it's going around, and so I don't know which direction the current is going, but when this flux is expanding, it is expanding across this conductor upwards in every direction.
Yes.
So when the current is increasing, the flux is in phase with it, so it's also increasing. So this flux would be cutting across. So if this conductor is going that way, so there's my conductor. This flux is expanding.
It's going into the cord?
Yeah.
Yeah. So if I split this in half, and I look at the one half of it, and say if the flux is going away from that conductor, it's like the conductor is moving in.
Yeah.
Okay? And the direction of the flux is this first counterclockwise direction that I gave you. So the conductor direction's against the flux, and the field is that way, and so the current should be going induced into the board.
Yeah.
Oh, God, lost me.
Right? So that means that this current is going like this, going around like this, through that way, and back. Okay, well let's try that then. Let's say, okay, if I use the left-hand rule again for this, it works for this as well. So you don't have to do that. Like you don't have to do the Fleming's left-hand rule with the 3 fingers. You can just say this actually works out that if the flux is going that way and I'm wound this way, yeah, the current actually does that. But where is the negative and where is the positive?
Opposite.
Negative.
Positive on top.
Negative bottom.
No.
Negative bottom, positive top.
Opposite to that, Michael. Why?
Darn.
Because it's
Because that's
going
the
in.
source. It's a source now.
source.
Right in.
And then the load would be negative to positive through the load. Now, when the flux is increasing, it's inducing voltage. Isn't the same thing happening over here on this first conductor?
Yes, yes.
When the current is increasing, I can do the same thing over here with this winding. And we know that induction always, and magnetic induction always opposes a change in current. So as the current is changing, the current is coming at you right now, right? Current is going this way, right? I'm just kind of said that's a 3D part of the conductor. I'm not a very good artist or whatever. So
You're good.
I'm trying, right? So that wire's coming around, it's coming at you because it's going to have to go this way, right? Oops, a little color. Right? Follow? That's because it was already connected to this source. So that means as that flux is expanding, you get that same thing happening on this side, and you can do the same analogy, and it means it's countering that. Because this one came at you, well that means that this one has a counter EMF doing that. But not totally to cancel out the first voltage, right? So as the current increases, as the value of current increases, this flux in the secondary actually causes a reduction in the counter EMF. What you're going to get is this one will cause a reduction in the counter EMF on the primary. Don't look at this. I got a handout that will be a little more clear. You know, the book used to actually have nice, clear, simple
I
diagrams.
studied that last night.
And they thought that it was too simple. So they thought they would throw this in and say, oh, well, here you go. Here's a better example. I think that this just muddies it up quite a bit. I don't even really use this. And if you really understand it, this makes sense. If you're just learning it, I think I got to give you some handouts that actually make sense.
So just try to prove there's a few.
Just go out to anyone to the end without, yeah.
Let's see. Here is
In the front.
here's the old learning task. So I'm going to give you guys that first. It used to be learning task 9, but it's now learning task 8. So it's the same one. Just you can compare the diagrams. It was just easy for me just to print it rather than try to figure out what pages it was.
Thank you. You're welcome. I was gonna do something.
Merci, Ricky.
Gracias.
It's
the same picture. It's the same picture. Pretty sure it's the same.
Well, technically.
Yeah, I know. On the examples, though. Going back to this red current here. Maybe I'll use the orange for the other flux. This flux that was established in this direction was based on the net current. The net current of the primary, right? There was no load connected.
Load's not connected.
It's pretty important, otherwise you're getting lost. Sure. Thank you. So without looking at this yet, just keep your eyes on the board here. With no load, an unloaded transformer, this flux is just magnetizing current. Right? That's just magnetizing current that produced that flux. What happens now is as the current increases in the secondary, it produces its own flux. So if you say that the current is going that way, it's producing a flux the opposite, right? The current is going the opposite, like, oh, hang on. It's supposed to be countering it. Anyway, maybe they've wired it right. Anyway, this flux, as this loads up, it causes a counterflux. So that difference between the flux is less flux, which means that there's less opposition to flow into the primary. So if there's less reactance, there's going to be more current. So what that does is that increases the primary current. So that's really what it does. As you load up the secondary, it reduces the flux in the core, which causes less inductive reactance, which means less inductive reactance means more current. So that's why the primary actually provides more current when the secondary also has more current. And it makes sense, the law of the universe is happy because you're using energy, you have to put energy in somewhere. So that's why it all works. Okay.
Is that like wasted energy though, or no?
Wasted?
Yeah.
No,
Okay.
except for copper losses.
The opposing flux increases the current of the primary?
Yes. Did I draw it wrong? Maybe
Even
I wound
though
it
it's
wrong.
increasing, counter EMF is, I don't know what I'm trying to say. Counter EMF restricts the amount of current, but the flux increases it
There's going to be less counter EMF in the
because
primary
of the flux.
if there's less flux, right? Less magnetic field, less Webers means there's less that it can react and produce. Like, what is it, BLV? Counter EMF is the same as a generated voltage, which is BLV. So if there's less B,
Yeah.
there's less counter EMF, right?
Oh, okay.
It's all related. Okay. Anyway, I may have drawn the windings wrong. I'm trying to, anyway. I tried.
A for effort.
Okay, so going back to this, we've already established this part in the previous learning task. Now what they're going to say is, okay, all these currents have a relationship, and all these voltage drops have a relationship. So if you maybe go to this new handout, you're going to see something very nice. Maybe not.
This in.
Okay, example, first example.
Is this learning task not? No?
Example 1.
It's just old.
Do I even have that? Overhead? I don't think so. How can I do it here?
I'm going to show my work for
Easier.
equation.
That's why this thing is so good.
Oh, the magnetizing.
Okay. Generated voltage. The primary voltage is here. And the generated voltage is there. Just got to analyze this a bit. So they've drawn it a little bit differently. They put the primary voltage to the left instead of to the right. So they've made their reference the generated voltage, which is the secondary induced voltage, on the right side, because that's the one they're using. So they made that right-hand arrow going horizontally to the right as the generated voltage, and that is actually the source on the secondary, and it also equals the counter EMF in the primary. So that's the same arrow for both. And they're saying that this one, the primary voltage, would be similar to the generated voltage in the secondary, but in the opposite direction. Okay, so it'd be negative. That would be negative generated. That would be negative to this EG. I can't use the cursor. It would be negative to this EG over here. Right? So that relationship is 180 degrees. So I've shown you that already. The two voltages are 180 degrees out of phase. because one reacts to the other, it's opposed by 180 degrees. So that means that the current, the magnetizing current in the source voltage here, the source voltage, the magnetizing current would be lagging that by 90 degrees-ish. And then what we have is, what is IE? What does it say IE is here? Can you find that? Center diagram?
Is that the current power?
I don't like the notations, but it's a simpler diagram at least. Okay. Nice. Thank you for that. It does say somewhere, it says IE and ICL, it says somewhere. Can you find that, guys?
Is that the
CL. I don't know why they use
the
these
first
stupid
on the
letters.
first page?
Maybe.
Is it the excitation current?
Excitation.
Excitation.
There you go. Yeah. And CL is to do with the coil. I think it means coil. Anyways, it's the resistive portion. Because there's resistance and there's also inductance. So it actually doesn't lag exactly by 90. There's a, well, I don't know why it's going that way, but anyway. Looks like it's leaking. We can do the next one. This is better. Let's just look at this. Okay. We have a load, a resistive load. If I have a resistive load on a transformer, how much current would that be? Well, I don't know. What's the voltage? So we're getting into voltage regulation. I think it's 240.
It's 240 volts.
240 volts. Okay, so a transformer has a no load voltage. At no load, when you read the voltage across the terminals of a transformer with your voltmeters, you grab your voltmeter and you measure it. You think it's going to be higher or lower normally than when it's loaded?
Lower.
Okay, there are losses, right?
Yeah.
There are drops
Oh, higher.
as the current increases. So your no load voltage is usually higher, right? Okay, so what they're trying to show here is that when you have a load, the transformer rating is rated for a specific power factor load and at full load. So when you see so many kVA, 30 kVA, 240 volts, it's based on full load. When it's no load, you should measure the voltage. When you wire up a transformer and you connect your voltmeter and you measure it to check it, it should read higher than what the full load voltage is. And then when you load it up, then you measure it again, it's going to be lower. The transformer actually drops the voltage itself with, you know, the load has a certain dropping down further as well, but we're talking about at the terminals, at the source terminals of the secondary. Okay, so this 1 ohm and point 4, those are out of phase, right? That's impedance. So we have a certain impedance in the transformer, so there's going to be an IZ drop across there because it's an internal impedance. Okay, so this voltage, what they're saying is, why am I using the mouse there? Ooh. So we got 4.8 ohms, and so let's look at this. What would it be at full load? It would be 50 amps, right? So at full load, the secondary is rated for 240. So at full load, we're going to say that it's 50 amps. That's going to be the rated ohms of load. So if it's a resistive load, it's going to be 50 amps. Okay. Now here's the vector for that. The reference is the current, and the total load is 240 volts. And it's in phase with the current. So because it's a resistive load, all the current is in phase with the voltage. Right, Ranveer?
Yeah.
Because why? It's in phase with the voltage because it's a resistive load. Yeah, you got to go and take a break or whatever you got to do. I'll just spiel it. Everybody can just leave and I'll just talk, and it'll all be great, I'll be happy with everything I said. You know? It's all good. The next one, and this actually makes it easier to understand. Where's example 2? That was example 2. Okay, so carrying on to this impedance of the transformer means that we dropped some voltage. So what they're showing you is what is the no load voltage if the resistive load brought it down to 240 volts. Well, that means you would have had to add back in the 2 drops, and they're out of phase. So if you add them back in, my actual voltage is now, at no load, would be the hypotenuse. And the output voltage would be smaller, it would only be 240. So in order to get that voltage, you have to add the drops back in at the same phasing that they exist. And that's how you're going to get whatever you get. So they said, okay, well we had 50 amps, and how many ohms do we have? Let me just flip that around again. 1 ohm and 0.14. So 50 times 1 is 50 volts, inductive drop. And 50 times 0.14 would be 7 volts, resistive drop. So they added those voltages back in to say, what would this produce if it had no load? So you're adding them back in. Does that make sense? You're adding back in the drops. I don't know why this is so difficult. So I added them back in. What did we get? It works out to 252. So what is the voltage regulation of this particular, at a resistive 100% power factor load would be, and these are just hypothetical numbers, but just to show you, they're trying to compare apples to apples. Here's the formula. The percent voltage regulation, this is going to come back on to level 3 as well. Percent E-reg
Yes.
is equal to no load minus full load divided by full load. Not no load, but full load.
You like
Is it
it?
always mine? It's 5%. Big squares in it.
Yeah, he's got squares.
Yeah.
I was wondering what the fuck those meant. Yeah.
Whoa, whoa, whoa. Language.
Come on.
Yeah.
Does anyone else have squares in theirs?
75.
Yeah, watch, I might have stepped on that.
What happened?
Page 75.
So this is the formula here. It's supposed to say voltage at no load minus the voltage at full load divided by the voltage at full load. Yeah, it's crazy.
Wow. Very slow.
Anyway, that's why you come to class. So anyway,
John Johnson D5.
so if I plug in the numbers, let me tell you this right now. You're going to automatically, by nature of automatic thinking, are going to probably want to put the bigger number in the bottom there. But it's always the full load rating that it's divided by. So you think about it, at no load I got 252 volts. I fire up the load, I turn on everything, 50 amps is running, it now drops down to 240. It's actually rated for 240. So what you have is the full load rating on the transformer says 240, but the no load rating is 252. So it ends up being the voltage regulation is 5% of the full load value. 5%. What is the voltage regulation? Not the percent, but just the voltage regulation? 12 volts. Yes. So this part here is how much it varies by. It goes from 252 to 240, so it varies by 12 volts difference from no load to full load. And that's called the voltage regulation.
Jeff, how much do you put there? What?
What is the percent voltage regulation. It's the voltage regulation divided by the full load voltage.
So you get a percentage, correct?
And it's a percentage. So it works out to 5% regulation based on the full load rating. Okay, anyway, that's that one. Now, I got a positive number here. Right, so we go 252 minus 240 divided by 240, so that's 12 out of 240, which is 5%, plus positive 5%. Okay, so that's how much that's what we get. So that's a normal situation. My mouse doesn't work on this thing.
That's like 3 times already.
Okay, let's look at an inductive load. Lagging power factor. Okay, now my load is 4.8 ohms. Same, 50 amps. But this 50 amps, because transformers are rated in VA, the transformer doesn't care when the current happens. It just happens. But does it? Does it matter for how much the voltage is regulating? Okay, so he's got, I guess it's Roger did this up. I don't know if his math is correct, but it probably is. So you got a 60% lagging power factor, meaning that you got 2.88 ohms of resistance and 3.84 ohms of reactance, right? So does that make sense right here?
Yes.
You got, yeah, because you've got, how's that work now? Yeah, because of this impedance of the load. This is the load. This is the load. So those would be the 240 volts is what's across this at full load. So we put the 240 there, and what would be the corresponding voltage triangle would be 144.
Pi thing.
Because that's
PR,
for you.
yeah, and VL would be 192. Okay, so now we've got those, that's your load. It's not in phase with the voltage, it's out of phase. It's actually lagging, right? So now you're going to take this, and you've got those same drops, that 7 volts and that 50 volts. You've got drops you're going to have to add back in. But instead of adding them just directly to a horizontal reference like a resistive load, you're going to add them to an angled drop. Okay, so let's look at how that looks. There's your voltage across your load, right?
Holy shit.
Right? This one? Makes sense? Okay. 240. You're going to add 7 volts, head to tail method. So there's the 7 volts across the drop across the transformer's secondary, the windings, right? The voltage drop across the windings. And then you flip the page, and you go step by step. You add the 50 volts in. So the generated voltage is not 252, it would have had to have been 285.2. Not that it will be, but what they're saying is, they're doing it in reverse because they're trying to compare situations and say, that means the output voltage at no load of the transformer would have to be way the hell higher in order for me to get 240 out. Most likely, it's just going to drop the voltage down further than 240. But they're just trying to compare and easy math and show you that this is how it works. So 285.2. So what is the voltage regulation on that? 18.8%. So try the numbers in your calculator, see if it's right.
So 45.2. Yeah, 18.83.
Okay, so what's the difference between a 50 amp resistive load, unity power factor, and a 50 amp lagging power factor load? What does it do to the voltage regulation of the output of the transformer? Does it drop down the output voltage, or does it make it better?
Makes it better.
If it's lagging, it's going to make
Damn
it
it.
worse.
50-50.
I was more extreme.
Huh?
I was more extreme.
More extreme, yeah. So if I had, let's say I had 252 as my main voltage, that would have to drop down like, what's the difference between this? 45.2? It would drop way down. So a lagging load, a motor load, say a motor load with lots of inductive capability, would drop that voltage right down. The transformer would react that way. So you always want to correct your power factor so that that doesn't happen, right? So that's one of the problems with Hydro's transformers, is if you have an inductive load, you're screwing with the output voltage to the consumer, or to yourself. You're lowering your available voltage at the terminals, because your load is sucking current from them, right? So it's happening that way. All right, move the mouse again. That's awesome. Okay, what about a capacitive load?
Okay.
We got the same example here,
Take a shot every time.
right? Except lead. So we've got the same math. This is why this is easier, because you're doing the same math. It's not like you're getting the new math going here. You still got the 50 volts. You still got the 7-volt drop. They're out of phase. You still got those two voltages. But what happens here? We say we've got the same 50 amps. Not that that would be the case, but it's more just to measure for an example here. But a leading power factor means that the current is leading the voltage in the load. So here's the current, here's the voltage of the load. The current comes before. So it's let's say it's a capacitor. We've got a capacitor running or something too much, overcorrection. So you overcorrected. Here's the problem with overcorrecting in the plant. Okay, so what you have is 7 volts, 50 volts. So let's go to the next page, see what we do here. Oh, interesting. Oh. We add the 7 to the 240, and then we add vertically the 50 volts, so we actually end up about here. And you work out the math, and it actually works out to 207.3 volts. That is the no-load voltage. Generated in every case here is the no-load voltage.
Oh, it's okay.
Right?
Negative.
So look at that, yeah, negative. So you have negative voltage regulation. 207 minus 240 would be a negative number. So even though we're going, what, 32.7 volts difference? Is that you guys?
That's
Bookstore? Okay.
32.7.
32.7, something like that, difference out of 240 full load voltage gives me negative voltage regulation. So what does that mean for hydro? Why don't they want you to overcorrect? What are you doing to their system?
Manipulating.
You have a source at your end called capacitive reactance, right? A capacitor, you're actually increasing the terminal voltage. So if this was 240, instead of 207, if this was 240 generated, let me think about this now. Yeah, then you'd be bumping it up to 37, 30, what did I say, 30 something?
32.7?
32.7, so if it was 240, then 32.7 is around 270 volts. So if you backfeed that through the transformer on the primary, you're bumping up that percentage of voltage to them.
Yeah, what is it?
That's really annoying.
Come on, guys.
Anyway,
I don't know.
so here's the deal.
You get credit.
Right.
It's the dealer phone.
Oh, yeah.
Should be.
So if your loads have a unity power factor, drops ET, terminal voltage. E-terminal, I'll put terminal. Where is that measured? Pretend this is a big transformer. This primary, it's measured on the secondary terminals, right? So the load would bring down the terminal voltage, it drops it.
That's a big transformer compared to that.
Lagging power factor, what is it, greatly drops terminal voltage. So even more so than a unity power factor resistive load. Leading power factor increases terminal voltage. And it's all to do with math. I can't really explain it any other way other than the capacitor is like a source. So it actually, because it's causing the current to lead rather than lag. Okay? I don't know, I figured the old way to explain it was a bit better, but whether it's no good for you either, I don't know. But I got another one here. I'm gonna keep one, just for myself, put up here. This one is from a level 3 handout for alternators, which is the same thing. You're producing a source, whether it's produced through a transformer or whether it's produced through a rotating machine, you're still producing a voltage. Here's a graph. Unity power factor, you can see that as you increase in load, it drops the output voltage. So you could almost call this, well, terminal voltage. Think of this not as stator current, but secondary current. I'm only giving you this because it actually is a better illustration of what's going on. They don't have it in your book.
Where is this one from?
This is from the handout I just gave you. Page 1, page 183. And this one here is if it's lagging. See, so what happens, you can see that the bigger the current, the more inductive that current is, the more it drops the output voltage. Leading power factor, to a point, will cause it to actually increase the terminal voltage. Okay? And the terminal voltage, what this point here is the, I guess where the generated voltage would be ideal at that point, right? The dotted line. And it's the same formula, just it's a generator. Ignore that and just think of it as a transformer secondary. Okay, and I think this one does a little bit better justice here. This second, the loads of power factor, I'm just going to zoom out. You can sort of see what I'm doing here. See this one?
Yes.
Yeah.
So at unity power factor, yes. Terminal voltage is from here to here. That means you would have to produce a higher voltage. What that little voltage drop, I'm just going to zoom in a little bit so you can see it. What happens when the current lags, this is actually a better diagram of the same thing. As the current lags, this resistive voltage, this little triangle here, is the same amounts, but it just pivots in line so that this ER is always in phase with this current. Right? And when the current goes up, what does ER do? It also goes up. So this little triangle, all it's doing, it's pivoting on this point. So you can see what it's doing is it's actually, if it goes down this way, it means the generated voltage had to be higher. If it flips up this way, the generated voltage had to be lower. You can see what's happening to the generated voltage. That one's probably a better diagram.
And Unity has an XL because it's just naturally in the coils of the transformer.
That's happening in the secondary coils of the transformer.
Okay.
Okay, that's what I wanted to kind of. Does that make more sense? No? Look at it at home, it'll make more sense later. We only have a limited time. Okay. Here's another one.
There goes the Amazon.
What do you gotta remember though?
There goes another chunk of the Amazon.
This?
Greg.
This. Just helping you understand it, that's all.
Sorry.
Nope,
What did you point to?
you're done.
I was turning back to hand up the, those two things.
And talking.
Ooh.
Hey, it's making it worse.
Okay, what it's saying is if I were to connect these two transformers in that way, I would end up getting a 96 volt output.
You do want that.
What they're showing you is that this is in phase, or out 180 degrees out of phase with the applied voltage. So just looking at this here, it gives you a little bit of write-up. Voltage and current relationships in a transformer. It says when the primary of a transformer is connected to power but there's no load to the secondary, current is limited by the inductive reactance of the primary. At this time, the transformer is essentially an inductor. And the excitation current, which is also the magnetizing current, is lagging the applied voltage by approximately 90 degrees. The primary current induces a voltage into the secondary. This induced voltage is proportional to the rate of change of current, which we know. The secondary voltage will be maximum during the periods that the primary current is changing the most, and it gives you the angles, 0, 180, and 360. That's in the sine wave, right? And it'll be 0 when the primary current is not changing, which is at 90 degrees and 270 degrees, right? If the primary current and secondary voltage are plotted, it will be seen in figure 455. So we'll go to 455. Right, so it lags. You can see the current lagging or leading?
Leading.
Oh, because which voltage is it?
Secondary.
Secondary voltage. Yeah, so where would the primary voltage be? Primary voltage would be the opposite of that secondary voltage. So they give you this other diagram.
How does that phase?
No, 180 degrees, yes. And they give you this diagram. Just to mess with you. So, okay, where's the primary voltage?
It's right there.
They don't have it. Oh yeah, apply. So now, if the voltage starts here, the current starts there, so the current is lagging, that must be the primary current. Yes, primary current.
Yeah.
So primary voltage and primary current right here. Okay. The other one, this one down here is the secondary voltage, which is 180 degrees induced, which is also the counter EMF's phasing, you could say, in the primary. It's in phase with the secondary voltage. And so the secondary current will be based on that induced voltage, which is 180 degrees out of phase with the primary voltage. Adding load. Then they go into this. They say when a load is connected to the secondary, current begins to flow. Because the transformer is inductive, the secondary current lags.
First page, and then it's changing.
Just going through with you. Secondary voltage by 90 degrees. Since the secondary voltage lags the primary current by 90 degrees, the secondary current is 180 degrees out of phase with the primary current. Wow. So, here's the kicker, right here, this last sentence. The current of the secondary induces a counter voltage in the secondary windings that is in opposition to the counter voltage induced in the primary. So if it's opposing the counter EMF in the primary, what is that doing to the current in the primary? Increasing it. So as you add load, it reduces the counter EMF in the primary and increases the current.
Because your resistance is going there.
Resistance is backward, but yes, your opposition, your counter EMF is decreasing.
Your Z.
Yeah. There you go. So you can put that in your pipe and smoke it.
I think it's 15 minutes early.
By smoking.
One try.
one never know.
We gotta get to the next learning test, so please be quiet. 9, right?
Yeah,
9?
niner.
Okay. We're not gonna get to calculations in this, but if I go to the,
Nine.
I usually like to be a little bit ahead of this at this point.
Just sold out right away.
9. Okay. Some transformers, guys, you wanted me to just let you do this at home and you can figure it out on your own? Or do you need anything? Do you need anything from here? To compensate for line drop and voltage regulation problems, because we talked about voltage regulation now, we know that as we add load, normally it's not going to be a leading power factor, it's going to be lagging, or unity, which is even rare, it's usually a little bit lagging, is what's preferred. But to compensate for that, transformers have adjustable turns ratios. So you can adjust the turns of the transformer so that it's not 200 turns to 100 turns. You might be able to adjust the turns in the primary by changing the tap positions in your transformer. Has anyone changed taps in a transformer?
Where is it?
It's on the, yeah, okay. I'll get a picture of one, but you know, I mean, there's taps in all kinds of transformers, even on control transformers to select different voltages. But what this does is if your voltage is too low coming in, like in Port Kells, really bad. Anyone do any work up in Port Kells area?
No, I used to work in Port Kells.
Okay, if you measure the voltage on a 208 volt panel, it's probably going to be like 197 volts or 198 volts. So what they do is they'll come in with a put a transformer in and put changeable taps on the transformer to bump up the secondary voltage so that it brings it back up to where it should be.
Why is it so low?
Because it's at the end of the grid. So like, especially during peak times when everything is running, they're at the end of the line. So it's like they've dropped down just because of the loading. And certain areas are like that. But we have here, in this case, you can see that 200 amps, if you have some resistance in a transmission line, how much voltage drop is that on each wire? Let's call it 0.6. And about 120 volt drop on both of those, added together?
Yeah, it's 60 each.
60 each, so 120 volt drop. Is that a huge percentage of 2400?
Yeah, I mean, it's a 20th.
Is it?
Yeah.
5%? Is that what's allowed? Is that 5%?
3%.
Is it 3 to 5?
That's what you're looking for, right? 5 sounds like a lot.
5 sounds like a lot. Okay, so try that. Go
24.
120 volt drop on my transmission wires. 2400 volts would be 120 volts out of 240.
Yeah, it's 20. 240 divided by 120 is
No, 120 divided by 2400.
5%.
Is it 5? Okay, so that might be a little bit high. Okay, you were right. The
First time ever.
You can see that on a secondary, that's 2000 amps. So what you have is this situation here, where a factory wired transformer will be at the which tap, do you think?
105, because you're losing stuff.
No.
Damn.
Anybody else?
102.5.
How about right where the cursor's pointed? You can see it.
Yeah,
100%. It's going to be on the 100% tap because they want the exact turns ratio to be there in case you have the correct voltage, rated voltage on both sides. Right? So what you can have is automatic. These are no-load tap changers. So what Hydro does is at their substations is if you had a no-load tap changer, you'd have to shut down the grid. You have to shut it down, and then you'd have to physically move it to the next tap, and then turn the load back on. So that's not very practical to have a no-load tap changer, other than maybe once in a while, you know, they notice that over time, more customers, more buildings have been put in, more homes have been built, the load has been increased considerably, so they say, okay, we need to put it to the next tap, so to bring the voltage up. So maybe it's a periodic change. That's the principle behind no-load tap changers. But what happens if it's during peak hours? So at nighttime, everybody shuts everything down, the current is less, so that means the voltage all of a sudden increases. So they want to bring the tap back. And then as dinner time comes around, everybody turns on their ovens, and then they also turn, whatever. Factories are during the day, and maybe they have night shift. And so it seems to be peak hours are anywhere from 4 to 7 p.m. And it's a huge demand on the grid. So what do? They got to change the tap the other way, so they bump up the voltage. So there's this continual thing all day that's got to go on. Well, then you need an on-load tap changer instead of a no-load, which is what this one is.
I would assume that would be like an automatic
And
changer.
we'll go through this in a sec. I'm just showing you the reason behind it. Where is it? Oh, did they talk about on-load? Yeah, here it is. On-load. So you don't have to shut her down. You basically can do it on the fly. It's like putting in a 4x4 mode on the fly, right? How does that work? Well, this one here has, when it's connected to 2 connection points, they have a reactor. So they have two connection points, and when it slides to the next one, it's going to have an air gap there, but it's still going to be connected, and then it's a make before break. But how do they get it so it doesn't short out between the 2 different voltages? I mean, that could be, over a high voltage situation, that might be, 100 volts or something. So why would you want, you wouldn't want it to short out. So what happens here is that when the current flows this way, and the current flows this way, the magnetic fluxes in the core of that reactor contact, it's a contact with a reactor attached to it, the fluxes cancel out, and it's just pure resistance of this winding, which is almost 0. But when you go between the 2, the current's now flowing in this direction, and there is no current flowing in that. This causes a magnetic field to be induced in the other side, and you end up with a reactance building up, which opposes that voltage, and it doesn't allow it to short circuit. So if the fluxes are going in the same direction, you got high XL. If the fluxes are going in the opposite direction, you got 0 XL. Right? Just like a wire wound resistor, we took the wire at both ends, halfway, and wound them around so that the currents are going, as long as they're going opposite, the flux would cancel. Right? So the flux is canceling here, but it's aiding here. And then when you get to the tap position, now it cancels itself again and becomes just a purely resistive contact, which better be almost 0, right? A good switch contact is always close to 0 ohms.
Figure B is like mid-change, right?
That's correct. Yeah. So what you're doing is you're going to the 97.5% tap. What about the no-load one? You guys follow this?
No.
So
It's a lot of wires.
you've got this situation here where you have to connect to 2 points at any given time, right?
Yeah.
So the reason why it's a no load is because there is a point where it's going to be not connected to 2. So you don't want to disconnect your circuit. Kind of like disconnecting an ammeter when the circuit is running, you're going to disconnect the whole circuit. Right? Then you got a park flash situation happen, you have to wear the full suit. You don't want to do that. So you shut it down, switch it to the next one. So in this position, which one is this? 3 and 4? You've got to follow the wires and see where you are. So I'm here and here. So it looks like these 2. So what they do, instead of taking it out of the outside of the winding, they take away the inner portions of the windings. Like,
When you're doing that, you wouldn't be able to, like you say you have to disconnect it, you wouldn't be able to disconnect it by just moving the dial correct. You'd have to completely take it off the source. Still?
this is
Yeah,
I
it's
went
just
back.
like a range changer kind of deal, like a rail.
Exactly. Yeah, I went back to the no load. Means that you cannot have it running. I did the other one first. So if you look at this, where would the full winding be, where would the connection have to be to use the full winding 100% of the times?
Can you scroll up?
4 to 5?
Oh, yeah. Better?
Or,
Oh, sorry.
Oh.
yeah, I'm going like 5 and 6 or whatever.
5 to 6?
One to two.
1 and 6.
It's
One
and.
The farthest left ones.
That's
I would
6.
assume.
So 1 and 6.
1 and 6.
And then, yeah, that one.
So up here.
Oh, is that one?
So you use the full winding if you went click, click, click up to here.
Oh.
Yeah.
And it would be labeled 100%. And then you go down to 97.5. And you go down to 95. Right? So generally it's 2.5% per change.
And that's just based on how many grid contacts there are.
You're actually eliminating part of the winding.
Yeah.
So think about this. If I had on the primary, if I had 1,000 turns, right? And then I went to, well, let's do 100 turns. And then I went to 97.5 turns. Let's go to 95. Say I go to 95 turns. Say I got, let's do it easy. I got 100 volts and 100 turns. How many volts per turn is that on the primary?
Uno.
Uno.
1 volt per turn. Easy math. What if I only used 95 turns?
We have 95 watts. I mean,
Volts per turn is.
How many volts per turn would it be?
Oh, it goes up.
Go, yeah.
Does
Does it go up
Volts.
0.05?
What's that?
1.05 volts per turn.
2.6.
So the secondary voltage, would it go up or down?
The voltage.
Wait.
Voltage
Down.
would-
Oh, it depends.
Oh.
What have you done to the volts per
You're going
turn?
up because you increase the volts per turn. You
Right.
get more.
Right. It's all about volts per turn with transformers. If you increase the volts per turn, then you increase the secondary voltage. Because usually the taps are put in the primary. And that's what we're going to do tomorrow anyway. We're going to do some calculations on that. So if you increase to 105%, what if I use the 105 turns? Okay, what are you doing now?
You would
It was
lower
95,
because
wasn't it?
decreasing the volts per turn.
How many volts per turn is that?
0.95?
0.95.
Mathematically?
0.95.
0.95? Okay,
Yeah.
I'm just going on your numbers.
Yeah, it is.
So that would do what to the output voltage?
Decrease it.
Yes. So if you have more turns, if you go to the higher percent of turns, you're actually decreasing the output voltage. If you go to a lower percent of the turns, you're increasing the output voltage because you've increased the number of volts you've produced per turn. Volts per turn, volts per turn. That's what you got to remember. Okay. Anyway, I think that's it for the day, guys. Thank you.
So I want the quiz for tomorrow. It's going to be 7 to 8.
Cannot hear you.
So the quiz for tomorrow.
7 to 9.
7 to 9.
Is it like. I probably know the answer. Is it half of that and half of the definitions?
Well, like I said, there's going to be questions like this with percent impedance, current calculation, and probably a regulation question, and probably a efficiency question, and the circuit test, test ball, that sort of thing.
But there's no one when calculation 105%.
No, not yet.
Because not
Not yet.
Oh, the short circuit thing?
Thank you.
Thanks, so.
Was that your question, sorry?
My question.
That was your question.